And now in this lecture we answer on two questions. In the first question, we'll find out the area of this rectangle ABCD, and in the second question, we will find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing, we have the big rectangle ABCD. Inside this rectangle, we have this semicircle. In addition, you know that line segment AP equals to 6 units in its length. This is line segment PC, that is equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the point of tendency of tangent DC with this semicircle. This point is point M. And we define the touching point of this semicircle with this side AB of this rectangle ABCD. This point is point E. We define the radius of this semicircle as X. And we join points O and M together by straight line. Point O is the center of this semicircle, point M is the point of the semicircle itself. Therefore OM is the radius of this semicircle that is equal to X units in its length according to our definition. Because of the fact that the radius OM that is equal to X, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, we created a quadrilateral MCBO. Inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral MOBC, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle not a square. So we relate to this quadrilateral MCBO as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle MOBC, side MO must be equal to the opposite side CB. But MO is X, therefore the opposite side CB must be also equal to X units in its length. In the next step, we join points P and A together by straight line. So by doing this construction, we can do peripheral angle APE. This is peripheral angle APE. OA is of course the radius of this circle that is X. OE is also the radius of this circle that is X. So peripheral angle APE subtends on A, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle is equal to 90 degrees in its size. So repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB equals to 90 degrees in its size. So we can implement rule 7 in our drawing. One, because the surrounding dimension before. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle APE must be equal to 90 degrees in its size. In the next step, we define this angle as alpha, and we will focus on the right triangle APE. Inside the right triangle APE, we have this angle that is alpha. This angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on the big right triangle, triangle ABC. Inside the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we will prove that the right big triangle, triangle ABC, is similar to the small right triangle APE. So write it down. We prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle APE. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC in the right triangle ABC, and it is equal to this angle, that is actually angle APE. In the right small triangle APE. So repeat again, we shall find out that angle ABC in the right triangle ABC equals to angle APE in the right triangle APE. They are both equal to 90 degrees, and therefore they are equal to each other. This is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the right triangle APE, and angle A also belongs to the big right triangle, triangle ABC. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle A, is it belongs to the big right triangle ABC, it will be defined as angle BAC. And angle A equals to itself. So if we relate to angle A, it belongs to the right triangle EPA, it will be defined as angle EAP. So repeat again, we shall find out that this equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore They are equal to each other. So this is angle BCA in the right triangle ABC, and it is equal to this angle, that is actually angle PEA in the right triangle EPA. So repeat again, I shall find that angle BCA in the right triangle ABC is equal to angle PEA in the right triangle EPA, and they are both equal to 90 degrees from each other, therefore they are equal to each other. So if we prove that all the three angles inside the big right triangle ABC are correspondingly equal to all the angles of the right triangle APE. And therefore those two right angles are similar to each other according to angle similarity rule. So I'll write it down. If we found out that the big triangle ABC is similar, this is the sign of similar, to the right triangle APE according to angle similarity rule. And from the fact that the big triangle ABC is similar to the small triangle APE, we derive that the following relationship exists between their sides. We derive the side AP of triangle APE over side AB of the big right triangle ABC is equal to side AE of the right triangle APE over side AC of the right triangle ABC. So repeat again, we derive that side AP of the right triangle APE over side AB of the right big triangle ABC is equals to side AE of the right triangle APE over side AC of the right triangle ABC. AP is 6, according to what is given us in the question, over AB. AB is the missing side, so we leave it as it is. And it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x over CA or AC. AC in total equals to 6 plus 5, that is 11. So in total we can find out that 6 over AB equals to 2x over 11. Here we will cross multiply this equation, and we get that 6 times 11 is equal to 2x times AB. 6 times 11 is 66, so 66 equals to 2x times AB. Here we divide this equation by 2 and we get that 66 over 2 is 33 and 2x over 2 is x. So in total, in this side of the equation we have x times AB. So 33 equals to x times AB. Here we divide this equation by x. It is allowable to divide the equation by x because of the fact that x is the radius of this semicircle. Therefore, x can never be 0. Therefore, it is allowable to divide this equation by x. So, we found out that AB equals to 33 over x units in its length. AB is the length of rectangle ABCD. It equals to 33 over x units. So our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. So in total, we shall find out that the area of rectangle ABCD equals to AB times CB. AB is 33 over X. And CB is X. So here we have X in the numerator and X in the denominator, so X will get cancelled and we left only with 33. So we shall find out that the area of this rectangle ABCD is equal to 33 square units. So we finished with the first question. In the next step, I will present to you the second question and we'll solve the second question of this lecture. In this second question, our mission is to find out the area of this grand shape. So in the drawing, we have square ABCD. We know that line 7 BP equals to line 7 PC. This is a triangle AEPOPC. This is equal to 5 square units in its size. Again, our mission is to find out the area of this grand shape. So, first of all, we define the length of BP as A. And because of the fact that BP equals to PC, if BP equals to A, therefore PC must be also equal to A. So in total, BC equals to A plus A, that is 2A. And because of the fact that all the sides of any square are equal to each other, therefore AD must be also equal to 2A. Those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to side BC. Those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC, and therefore they are equal to each other according to Rule 15. Rule 15 says that alternating angles between parallel lines are equal to each other. So if we define the size of this angle as beta, then this angle must be also equal to beta because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the parallel lines AD and BC. That is to say, AD is parallel to BC. So if we define this angle as alpha, then this angle must be also equal to alpha because they are equal to each other according to Rule 15. So if we found out that the small triangle COP is similar to the big triangle ADO according to angle similarity rule. Those two angles are both equal to theta, those two angles are both equal to alpha, and those two angles are both equal to beta. So I write it down. If we found out that the big triangle ADO, this triangle ADO, is similar, this is the sign of similar to this small triangle COP according to angle similarity rule. And now we present to you a new rule, and we will implement the new rule in our drawing. The new rule is Rule 22. According to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their sides. So in the drawing we have those two triangles, triangle ABC and triangle DEF. Those two triangles are similar to each other, and therefore the area of triangle ABC over the area of triangle EDF is equal to the square of the ratio of their corresponding sides. That is to say, here side AB is the corresponding side of side DF. So it is AB over DF squared. Likewise, side AC is the corresponding side of side DE, therefore it is AC over DE squared. And finally, side CB is the corresponding side of side EF, and therefore it is CB over EF squared. So repeat again, the ratio between the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. So in the next step, we will implement Rule 22 in our drawing. We have found out that the big triangle AOD is similar to the small triangle OPC. Therefore, according to Rule 22, we will get that the area of the big triangle ADO over the area of the small triangle COP. So the ratio between the areas of those two triangles is equal to the square of the ratio of their corresponding sides. Here side AD is the corresponding side of side PC. So it is AD over PC squared. So according to Rule 22, we actually found out that the area of triangle, the big triangle ADO over the area of triangle COP is equal to AD over PC squared. This equation is the implementation of Rule 22 in our drawing. The area of the big triangle ADO is unknown, so we leave it as it is. So it is the area of the big triangle ADO over the area of this small triangle COP. It is given us the equation that the area of this small triangle COP is 5 square units, and it is equal to AD. AD is 2A over PC. PC is A squared. So today we found out that according to Rule 22, the area of triangle ADO over 5 equals to 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled. After we cancel A, we left only with 2 squared. So 2 squared is 4. So in total, we found out that the area of triangle ADO over 5 is equal to 4. Here we multiply this equation by 5, and we get that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. So if we found out that the area of this big triangle ADO is equal to 20 square units, so I'll write it down. The area of this triangle ADO is equal to 20 square units. And because of the fact that the big triangle ADO is similar to the small triangle COP, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle COP is equal to side AO of the big triangle ADO over side OC of the small triangle POC. Repeat again, from the fact that those two triangles are similar to each other, we derive that the following relationship exists between their sides. That side AP of the right triangle, side AD of the right triangle ADO, this letter is D. So side AD of triangle ADO over side PC of triangle POC is equal to side AO of triangle ADO over side OC of triangle POC. AD is 2A over PC. PC is A. And it is equal to AO over OC. So in total, we found out that two A over A equals to AO over OC. AO over OC. We have A in the numerator and A in the denominator, so A will get cancelled. We left in this side of the equation, we left only with 2 equals to AO over OC. Here we multiply this equation by OC and we get that 2 times OC equals to AO. We define OC as B, so we substitute OC by B in this equation, and we get that 2B equals to AO. So today we found out that if OC equals 2B, then AO is 2B. So OC equals to B units in itself, and if OC is B, then AO equals to 2B. That is to say, AO is twice as big as OC. Okay. So in the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is true in any triangle, so this is triangle ABC that could be in any triangle. So if we draw the red line OP on BC, we divide this triangle ABC into 2 parts, or 2 smaller triangles. The first small triangle is APC and the second small triangle is APC. Again, the first small triangle is APP and the second small triangle is triangle APC. And the ratio between the areas of those 2 triangles, that is to say, the area of this triangle ABP is the base of the triangle that is BP times the height that is edge over 2. The ratio of the area of this triangle APC is the base of this triangle that is PC times the height that is edge. Both triangles have the same height that is edge over 2. Again, the area of this triangle APC is the base PC times the height that is h divided by 2. Now the ratio between the areas of those two smaller triangles, that is to say the area of triangle ABP over the area of triangle APC, is the area of triangle ABP is BP times h over 2, while the area of triangle APC is equal to CP times h divided by 2. So we have 1 half in the numerator and one half in the denominator, so 1 half will get cancelled. We have h in the numerator and h in the denominator, so h also will get cancelled, and we left only with BP over CP. That is to say, when you divide triangle ABC that could be any triangle into two parts, then the ratio between the smaller triangles is equal to the ratio between the bases of the smaller triangles. Because why? Because BP is the base of triangle ABP and PC is the base of triangle APC. So the ratio between the areas of the smaller triangles is equal to the ratio between the bases of the smaller triangles. So we can implement the new rule in our drawing. One, because in our drawing we have this is the right triangle, triangle ADC, and we have this is line segment DO that divides the big right triangle ADC into two smaller triangles. The first small triangle is ADO and the second small triangle is DOC. So according to the new rule, the ratio between the areas of those two smaller triangles is equal to the ratio between the bases of those two smaller triangles. We will choose the base of this triangle ADO as AO, and we choose the base of this triangle COD as OC. So according to the new rule, we get that the area of this triangle ADO over the area of this triangle COD again, the area of triangle ADO over the area of triangle COD is equal to the ratio between the bases of those two triangles. We choose the base of triangle ADO as AO and the base of triangle COD as OC. So in total, we found out that according to the new formula, the ratio between the area of triangle ADO over the area of triangle COD is equal to the base of triangle ADO over the base of triangle COD. That is to say, it is AO over OC. We have only found out that the area of this triangle ADO is 20 square units over the area of this triangle COD. The area of this triangle COD is unknown, so we leave it as it is. And it is equal to AO. AO is 2B over OC. OC is B. So we found out that according to the new rule, the 20 over the area of triangle COD equals to 2B over B. So we have here B in the numerator and B in the denominator, so B will get cancelled. And we left only with 2. This side of the equation. So in total, we actually found out that 20 over the area of triangle COD is equal to 2. So here we will divide this equation by 2 and we will multiply this equation by COD simultaneously. And we get that 20 over 2 equals to the area of triangle COD. 20 over 2 is 10. So in total, we should find out that the area of triangle COD is equal to 10 square units. So the area of this small triangle COD is equal to 10 square units. The right triangle ABC can went to the right triangle ADC according to side rule. Know that ABCD is a square, so all of its sides are equal to each other. Therefore, side AB of triangle ABC is equal to side DC of triangle ADC. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC. And finally, side AC is a common side that belongs to both triangles. So we can write down that AC equals to itself is a common side that belongs to both triangles. So finally, we found out that they have the triangle ABC can go into this triangle ADC according to side rule. So I write it down. We found out that triangle ABC, the right triangle ABC, congruent, this is the sign of congruent, to the right triangle ADC. According to side rule. All the three sides of triangle ABC are correspondingly equal to all the three sides of triangle ADC. Therefore, the two right triangles are similar to each other according to side rule. And from the fact that they are similar, therefore the right triangle ABC can point to the right triangle ADC according to side rule. And from the fact that those two triangles are similar, that those two right triangles are similar to each other, we will derive that they have also the same areas. That is to say, the area of the right triangle ABC is equal to the area of triangle ADC. Whenever you have two triangles that are congruent to each other, they must have also the same areas. But we know that the area of this triangle ADC in total it is equal to 20 plus 10, that is 30 square units. So we can write down here that the area of triangle ADC is equal to 30 square units. You can see it easily from the drawing. And from this equation, the area of triangle ABC equals to the area of triangle ADC, and it is equal to 30 square units. We will derive that the area of triangle ABC is also equal to 30 square units from one side, but from the other side, if we define the area of this green shape as x square units, then the total area of triangle ABC will be equal to x plus 5. So from the other side, the area of triangle ABC, the right triangle ABC, is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We derive that x plus 5 equals to 30. So here we will subtract 5 from this equation and finally get that x equals to 30 minus 5, that is 25. So x equals to 25 square units in its length. So we found out that the area of this green shape, x is equal to 25 square units. So in the next step, so we finish with the second question. In the next step, we'll summarize the lecture. We'll start with the first question, of course. mission in this first question is to find out the area of this rectangle ABCD. So in the drawing we have a rectangle ABCD. Inside this rectangle ABCD we have this semicircle. In addition, we know that this is line segment PC that is equal to 5 units in its length. This is line segment AP that is equal to 6 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle ABCD are right angles. In the next step, we define the center of this semicircle. This point is point O. We define the point of tendency DC with this semicircle. This point is point M. And finally, we define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. In addition, we also defined the radius of this semicircle is X. And we join points O and M together by straight line. Point O is the center of this semicircle, point M is the point on the semicircle itself, therefore OM is the radius of this semicircle that is equal to X units in itself according to our definition. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do quadrilateral MCBO. Inside this quadrilateral MCBO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total it must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral MCBO we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to this quadrilateral MCBO as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MCBO, side MO must be equal to the opposite side CB. But MO is X, therefore CB, the opposite side CB, must be also equal to X units in its length. In the next step, we join points P and A together by straight line. By joining points P and E, we get the peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle APE that subtends on AE, that is the diameter of this semicircle, is equal to 90 degrees in its size according to rule 7. In the next step, we define this angle is alpha, so in the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha according to the third rule that says that the sum of the angles in any triangle is equal to 180 degrees. So actually this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A belongs also to the small right triangle AP. So angle A is a common angle that belongs to both triangles. In the next step, we prove that the big right triangle ABC is similar to the small right triangle AEP. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle A, that is a common angle that belongs to both triangles, so we can write down that angle A equals to itself is a common angle that belongs to both triangles, and finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can found out that all the figures of the right triangle ABC are correspondingly equal to all the figures of this right triangle APE, and therefore those two right triangles are similar to each other according to angle similarity rule. Repeat again, we found out that the big triangle ABC is similar to the small triangle APE according to angle similarity rule. and for the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of triangle APE over side AB of the right triangle ABC is equal to side AE of the right triangle APE over side AC of the right big triangle ABC. Repeat again, we will derive that side AP of triangle APE over side AB of the big right triangle ABC equals to side AE of triangle APE over side AC of the big right triangle ABC. AP is 6, AB is the missing side, so we leave this it is. AE is the diameter of this semicircle, that is 2x. A is 2x. And AC in total equals to 5 plus x, that is 11. So AC equals to 11. So total we found out that 6 over AB equals to 2x over 11. If we could multiply this equation, we found out that 6 times 11 equals to AB times 2x times AB. 6 times 11 is 66, so 66 equals to 2x times AB. If we divided this equation by 2, and finally found out that 66 over 2 is 33, 2x over 2 is x, so in total this expression equals to x times AB. So in total we found out that 33 equals to x times AB. If we divided this equation by x, and finally found out that AB equals to 33 over x. This is 9 cm AB or side AB, that is equals to 33 over x units. Our mission is to find out the area of this rectangle ABCD. We have to find out the area of rectangle ABCD. Actually, we know that the area of a rectangle equals to the length of the rectangle times the width. Therefore, the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The width and the length is AB, and the width is BC. Therefore, in total, the area of triangle ABC must be equal to the length AB times the width, that is CB. AB is 33 over x, and CB is x. So the area of triangle ABC equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So actually found out that in total, the area of this rectangle ABCD is equal to 33 square units. So we finish with the first question. In the next step, I presented to you the second question, and solve the second question of this lecture. Our mission in the second question is to find out the area of this green shape. So in the drawing, we have square ABCD. We know that line segment BP equals to line segment PC. In addition, we know that this is a triangle POC, and the area of this triangle POC is equal to 5 square units. Again, our mission is to find out the area of this green shape. So we define the length of BPSA, therefore, because of the fact that BP equals to PC, therefore PC must be also equal to A, and because of the fact that ABCD is a square, all of its sides are equal to each other. Side BC equals to 2A, therefore side AD must be also equal to 2A. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. In addition, we know that the opposite sides of a square are parallel to each other. So in square ABCD, side AED is parallel to side BC. Those two angles are defined as alternating angles, and they are located between the parallels AD and BC, and therefore they must be equal to each other. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 15. According to Rule 15 states that alternating angles between parallels are equal to each other. So if this angle is beta, then this angle must be also equal to beta according to Rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the parallels AD and BC. And therefore, according to Rule 15, they must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha, because according to Rule 15, they are equal to each other. So all the three angles of the big right triangle A or D are correspondingly equal to all the three angles of the small triangle POC. And therefore, those two triangles are similar to each other according to angle similarity rule. Repeat again, we can find out that the big triangle ADO is similar to the small right triangle COP according to angle similarity rule. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule 22. According to rule 22, the ratio of the areas of similar triangle, the ratio of the areas of similar triangles is equal to the square of the ratio of their sides. So in the drawing, we have triangle ABC that is similar to the small triangle DEF. So those two triangles are similar to each other. And according to this rule 22, the ratio between the areas of those two triangles, that is to say the area of triangle ABC over the area of triangle DEF, is equal to the square of the ratio between their corresponding sides. So in this drawing, side AC is the corresponding side of side DE, so it is AC over DE squared. Likewise, in this drawing, side AB is the corresponding side of side DF, and therefore it is AB over DF squared. And finally, side CB is the corresponding side of side CF, and therefore it is CB over EF squared. So we can actually implement rule 22 in our drawing. Why? Because in our drawing, we already found out that the big triangle ADO is similar to the small triangle POC. So according to rule 22, the ratio between the areas of those two triangles, that is to say, the area of triangle ADO over the area of triangle COP, it is equal to the square of the ratio of their corresponding sides. Here, side DC is the corresponding side. Here, side AD is the corresponding side of side PC. Again, side AD of triangle ADO is the corresponding side, is the corresponding side and to side PC. Again, side AD is the corresponding side of side PC, and therefore it is AD over PC squared. So the ratio between the areas of the two triangles, that is to say, it is the area of triangle ADO over the area of triangle COP equals to the square of the ratio between their corresponding sides. That is to say, it is AD over PC, because AD is the corresponding side of PC, and therefore it is AD over PC squared. So this equation is the implementation of rule 22 in our drawing. The area of triangle ADO is the missing area, so we leave it as it is. Over the area of triangle COP, it is given us the question that the area of this triangle COP is 5 square units. So we substitute the area of triangle COP by 5, and it is equal to AD. AD is 2A over PC. PC is A. Again, AD is 2A, PC is A squared. We have A the denominator and A the denominator, so A will get cancelled. And we left only with 2 squared. 2 squared is 4. So in total, we actually found out that the area of the big triangle ADO over 5 equals to 4. So here we multiply this equation by 5 and finally found out that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. That is to say, the area of this big triangle ADO is equal to 20 square units. Okay, because of the fact that triangle ADO is similar to triangle POC, the following relationship exists between their sides. Side AD of triangle ADO over side PC of triangle POC is equal to side AO of triangle AOD over side OC of triangle COP. And repeat again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of triangle ADO over side PC of the small triangle COP is equal to side AO of triangle ADO over side OC of triangle COP. AD is 2A over PC is A. We have AO over OC. We have A the denominator and A the denominator, so A will get cancelled and we left only with 2, that is equals to AO times OC. Here we multiply this equation by OC and finally found out that 2 times OC equals to AO. If we define the left of side OC as B, and so we can substitute OC as by B here in this equation, we get that 2B equals to AO. So if according to our definition OC is B, then OA must be equal to 2B. That is to say, OA is twice as big, OA is twice as big as OC. So if OA is B, then again, if OC is B, then OA is 2B. Okay. In the next step, actually, presented to you a new rule, and we implemented the new rule in our drawing. We call to the new rule, Rule 23. According to Rule 23, Rule 23 is true in any triangle. So in a triangle ABC could be any triangle. If we draw this red line segment AP, by drawing the line segment AP, we will divide the triangle ABC into 2 smaller triangles. The small triangle ABP, that is the first triangle, and the second triangle is triangle APC. The area of triangle ABP equals to the base BP times the height that is edge over 2. The area of triangle ABP equals to the base BP times the height that is edge over 2. While the area of this triangle APC, the small triangle APC, is equals to the base that is PC times the height that is edge. Both triangles have the same height over 2. So it is the base PC times the height that is edge divided by 2. So the ratio between those two triangles, the ratio between the areas of those two triangles, that is to say the area of triangle ABP over the area of triangle ABC, is equal to BP times edge over 2 over CP times edge over 2. Here we have 1/2 on both sides. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. We have edge in the numerator and edge in the denominator, so edge also will get cancelled, and we left only with BP over PC, BP over CP. So in total we should find out that whenever you draw a straight line in triangle ABC, that could be any triangle, a straight line AP on BC, you will divide the triangle ABC into 2 smaller triangles. The ratio between the smaller triangles is equal to the ratio between their bases. The ratio between the areas of the smaller triangle is equal to the ratio between their bases. That is to say, the area of triangle ABP over the area of triangle APC equals to the base of triangle ABP, that is BP, over the base of triangle APC, that is CP. So we can actually implement Rule 23 in our drawing. Why? Because in our drawing we have the big triangle ADC. This is the big right triangle ADC, and we have line segment OD that divides the big right triangle ADC into 2 parts, into 2 smaller triangles. The first small triangle is triangle ADO, and the second small triangle is triangle ODC. Therefore, all the requirements of Rule 24 are satisfied, and therefore we can implement here Rule 23. According to Rule 23, the area of this triangle ADO over the area of this triangle OCD will be equal to the base of this triangle ADC, that is AO, over the base of this triangle OCD, that is OC. And again, we should find out that according to Rule 23, the area of the small triangle ADO over the area of the small triangle COD is equal to the base of triangle ADO, that is O over the base of triangle COD, this is OC. So in total, we found out that the area of triangle ADO over the area of triangle COD equals to AO over OC. We have already found out that the area of this triangle ADO is 20 square units. So we substitute the area of triangle ADO by 20 over the area of triangle COD. The area of triangle COD is the missing area, so we leave it as it is. And it is equal to AO. AO is 2B. So we substitute AO by 2B over CO. CO is B, so we substitute CO by B. So in total, we found out that 20 over the area of triangle COD equals to 2B over B. We have B in the numerator and B in the denominator, so B will get cancelled, we left only with 2. So in total, we found out that 20 over the area of triangle COD equals to 2. Here we divided this equation by 2 and multiplied by the area of triangle COD simultaneously, and found out that 20 over 2 equals to the area of triangle COD. 20 over 2 is 10, so in total we found out the area of the missing triangle COD is equal to 10 square units. That is the area of this triangle DOC is equal to 10 square units in its size. Here, the right triangle ADC is similar to this right triangle ABC according to side rule. That is to say, side AD of triangle ADC is equal to side BC of triangle ABC, because ABCD is a square, all of its sides are equal to each other. In addition, side DC of triangle ADC is equal to side AB of triangle ABC, because of the same reason, because ABCD is a square. And finally, side AC is the common side that belongs to both triangles. So we can write down that AC equals to itself is the common side that belongs to both triangles. So if we found out the triangle ADC can go into triangle ABC according to side rule. Repeat again, if we found out that triangle ABC can go into triangle ADC according to side rule. And from the fact that the two triangles are similar to each other, we will derive that they have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. Remember, you have two triangles that can go into each other, they must also have the same areas. So the area of triangle ABC must be equal to the area of triangle ADC. But we know that the area of triangle ADC in total equals to 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC equals to 30 square units. And from this equation, the area of triangle ABC is equal to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square units from one side. But from the other side, if we define the area of this green shape as x, that is to say the area of this green shape equals to x square units, then the area of triangle ABC in total will be equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30, we will derive that x plus 5 equals to 30. Here we subtract 5 from this equation and finally get that x equals to 25 square units. So the area of this green shape that is equal to x square units is equal to 25 square units. So in total, we found out that the area of this green shape is equal to 25 square units. And that is the answer to the question. Okay, thank you very much.